Hello, everyone. Welcome to the lecture 8 of the Deep Learning for NLP course. Today, we discuss about encoder-decoder models. Specifically, in this lecture, I explain encoder and decoder architecture, and then we talk about the attention mechanism. As usual, at the end, we discuss about applications of such an architecture and the attention mechanisms in NLP. Let's just start with encoders. Encoder is a neural model to transform a text into a vector in an embedding space. So if we have a piece of text like what we see here in the figure, we can feed the text into the encoder, and encoder is a neural model, and then it maps this text to a vector of numbers. So far in this lecture, we have seen different types of neural encoders, such as pre-trained word embeddings like glove, word to wake, bird, and so on. Any of these pre-trained word embeddings can be used to transform texts to some vectors. For example, glove or word wake can be used to transform words to some vectors, and then you can so you can compute the mean. Actually, you can run a mean pooling over the word vectors of words in a sentence, and then you can get the sentence representation, right? Or if you use more advanced architecture like a bird, so you can give it a piece of text as the input and it returns contextualized representation of the text. And in the last lecture, we discussed about RNNs. So you can use RNNs over word embeddings to obtain vector representation of a sentence. So different types of neural models can be used as encoders, like multi-layer perceptrons, convolutional neural networks, or CNNs, recurrent neural networks, or RNNs, and transformers, which will be discussed later in the course, probably in next few lectures. Okay, now that we know what an encoder is, we can discuss decoder. A decoder is a neural model to transform a vector from an embedding space to a text. So if we have a vector in an embedding space as the input, the decoder takes the vector and tries to map that to the language, to a text. So different types of language models can be used as decoders. Like RNN-based language models and transformer-based language models. So decoders, the main goal of decoders is to generate a text, right? So the input vector can be seen as the context. So you are given a context, or you are given a vector representation of the context, and you want to transform this vector to some texts. Usually what we do is that we try to generate words one by one or word by word. And at each time, we try to use the information of the context to generate word. And whenever we are dealing with generating a word or with generating a text, we usually use language models, right? The task of the language model, if you remember, was to estimate the probability of a sequence of words. And in that lecture, that was about in the lecture that was about language model, I discussed how we can use language models to generate a text, right? So as decoder component, we usually use language models. And since we are talking about neural networks, we probably prefer to use neural language models like RNN-based and transformer-based language models. Okay, given an encoder and decoder, an encoder-decoder architecture looks like this figure. As the input to the encoder-decoder architecture, we have a text. So we give it to the encoder and we map that to a vector to which we refer as context vector. And then we use a decoder on top of this vector to transform the vector to a piece of text. The point is that the input text and output text could be or could not be identical, or even they can be from one language or they can be from different languages. So the main goal of this task is to move from a text to a text. We want to start from a text and we want to end to a text. In this way, if you train the parameters of the encoder and decoder together, you are doing end-to-end learning. Why? Why is it end-to-end? Because the main goal of natural language processing is to communicate with computer using human languages, right? So if we can use our input text, and as the output text, we also get some, as the output, we also get some texts, then we can train this model end-to-end. We can train this model from text labels. For example, in machine translation, if we want to translate a sentence, so we don't need to know which word is assigned to which word or something like this. So the only thing that we want to know is that the translation of this word or the translation of this sentence in a source language is Y or output text in the target language. So if we are given these pair of sentences, one in which one element or the first element is the sentence in the source language and the second element is the sentence in the target language, then we can use this first sentence as the input and the last or the second sentence as the output text in an encoder-decoder architecture, and we can train the model end-to-end. So we can say from this input text, we should move to this output text. So this is end-to-end, right? In this, so in the end-to-end training, we train whole parameters of encoders and decoders. However, if we train each component one by one, so if we say, okay, for this source language, we need to train encoder first. So let's say we train some RNNs independently and we save the parameters somewhere. And we train also a decoder somewhere else. So we train a language model in the target language on a lot of documents or a lot of sentences in the target language. And then we take these two pre-trained encoder or these two pre-trained models, one encoder and one as the decoder, and then we connect these two models together, then we are training the models or we are dealing with a model that is trained in a pipeline fashion. The weakness of the pipeline fashion is that if you have some errors in the decoder or encoder, you are propagating this error through the components. So if the encoder makes 80%, or let's say if the encoder is 80% accurate, then you cannot expect that the performance of the whole model gets over 80%, right? Because for 20% of cases you make a mistake by encoder because of your encoder, and this error propagates through the other components like the decoder that we have in encoder decoder architectures. But on the other hand, the disadvantage of the end-to-end training is that you need a lot of data to train the whole parameters of the model, because you need to learn two tasks. You need to learn encoding and decoding part. You need to understand the text first. You need to understand the text from the source language first, and also generate a correct sentence in the target language. So it's like two difficult tasks, and your goal is to learn it automatically. Yeah, so the main idea behind end-to-end then is to learn a task end-to-end, so we don't care what components we need. So we assume that a neural model like encoder-decoder can learn it automatically. We can, an encoder and a decoder can learn to move from one language to other language. But in pipeline architecture, we try to help the model. So we say, okay, so we train this model or encoder first, we train the decoder first, and we use these pre-trained models to make our encoder-decoder architecture. So you can play a lot with this encoder-decoder architecture, but the main building block in encoder-decoder, it looks like this. So you have an input text as the input, you give it to the encoder, and the task of the encoder is to map the text to some vector, to one vector, and then we take this vector and we use it as the output text. And maybe try to decode the text from that. Okay. But let's assume, as we discussed, we can have different sorts of encoders. Let me focus on RNN encoder first, as it is discussed in the previous lecture. So as the input, we are given a sequence of vectors like x1, x2, and x3. If you remember, if we assume we have 3 words like x1, x2, x3, and we can use some embedding layers to map these vectors to some word embeddings. And when we use vectors or matrices, we use boldface to refer to these variables. Okay, so the task of the RNN was like sequentially processing the input sequence. So we take x1 and we generate a hidden state. I don't use weights here because, I don't show the parameters here because we can use different types of RNNs. We can use LSTMs or GRUs, but here we focus on the architecture of the RNN. So as the input, we get x1 as the input, and we generate a hidden state. We don't care about the output because the task of the encoder here is only to generate a context vector. It's not going to generate an output after each step. So we are not doing any sequence tagging. Then we take the second input and we generate the second hidden state, and we take this third input and we generate the last hidden state in the phrase that we are given. Okay, so, and if we remember, we discussed that at each time step, the hidden state represents the whole sequence from the first token until the current token. So at the last token, we expect that in theory, or in principle, H3 should represent the whole sequence from X1 to X3. So, so let's say we directly take H3 or the last, or the hidden state in the last step as the context vector, all right? So, and an RNN decoder can look like this. So we give it like, we give like a start of a string or a start of sentence as the input. So as like the initialization token. So this is the first token. So we said we want to start a sentence. We give it to the hidden state that can be initialized by any vector. And if you remember in the previous lecture, we usually initialized H1 in the decoder, or in H1 in RNN architecture by 0 vector. But for now, I keep it open so we can initialize it with any value that we want. But we will discuss how or what would be the value in the next slide. But let's assume that we have some initialization of H1, and as the input, we take SOS, and or a start of the string. And then we generate a token as the output, like, or at least a probability distribution of over vocabularies in the language for the first step. Okay, and then we use the word that we generated in the first step as the input to the second hidden step, right? And then based on these words and the previous hidden state, we generate the second word, and and we use the second word or the second generated word as the input to the third step, and we generate the hidden state, and conditioning on this hidden state, we generate the third word. So we can generate a sequence of words using decoder. Okay, so if you connect your context vector to add, okay, so now we are given a text like x1, x2, x3. So you can use the last hidden state in the encoder as the context vector, and then you feed this context vector to your decoder as I mean, some sort of initialization for h1, or like the initialization for the hidden state at the first step, and then you can generate words in the decoder one by one. Okay. RNN-based encoder-decoder architectures is very useful for different NLP applications. However, we can see some problems here. First, the context vector is used to initialize the hidden state of the decoder, right? But it means its impact vanishes at the last steps of the decoder. Let me show you this slide again. As you can see here, we encode the input text x1 to x3 to one vector, which is the hidden state at the last step. And then we feed this vector to the first hidden state, right? So we feed it to h1. That's it. So we are done. But after that, we never look back at this context. So we assume that the RNN-based decoder can capture this information through the whole steps. But we know vanishing gradient happen and so on. I mean, we know about these problems. Beside these problems, when you feed it to h1, you do not have any direct impact on h3 and h2 in the decoder phase. So what can we do to bring it or emphasize on this context information? So the idea is very simple. So what we can do is just to use this context as the input to the hidden states in the decoder. So what we do is mainly concatenating this vector to the input vector to the encoder, to the decoder part. So we concatenate this context vector to the input vector, and then we use it as the whole input to the decoder. Okay. As we discussed, the output of the encoder is known as the context vector. The dimensionality of the context vector is fixed, right? So if, for example, in this architecture, the dimensionality of the context vector is equal to the dimensionality of the hidden state in the encoder. So and as we discussed in the last or in the previous lecture, the dimensionality of the hidden state in RNN is a hyperparameter. So if you set it to 100, it means you use a vector with 100 elements as the hidden state. And therefore, the size of your context vector is also 100. So by the way, it's fixed. So no matter how long your input text is, you want to map it to a vector with 100 numbers. So if you take a sentence with 3 words, you map it to a vector with 100 elements. And if you take a sentence with 300 words, you want to map it to a vector with 100 vector numbers. So different input texts might have different lengths, right? So considering the hidden state of the RNN encoder may not capture the entire input text. So if you, therefore, it's kind of very difficult for the encoder to capture the whole information of especially long input sentences into a vector named context. So this is especially a problem for long input texts. So how can we solve this problem? What can we do, or what we can do is that instead of taking the last hidden step as the last hidden state as the context vector, we can use the average over all hidden states in the encoder. So we compute the average over all hidden states in the encoder, and we take the output of this average function, or the mean pooling, as the context vector. And then we feed this context vector to all the hidden states in the decoder. Oh yeah, I'm noticing that here H3 should have a D here to indicate that this hidden state is dedicated to the decoder. Okay, so I correct this notation here after the video, and I upload the slides again. But I mean, it doesn't impact the idea, just it's like the matter of the notations. Okay. Yeah, so other than that, so I guess our focus should be here, that we discussed two types of methods for capturing the context vector. The first one is to take the hidden state at the last step to represent the context vector, or to represent the whole input text. And the second method is to compute the average over all hidden states in the encoder. So one of the nice things about this approach is that if you compute the gradient of, or when you are propagating the gradient, when you get the gradient at this step, you propagate it through all hidden states equally, right? So the vanishing gradient will not happen here because you have some sort of escape connection. So it doesn't matter. So in the normal case, in the last hidden case, or in the first method, when we use the last hidden state as the input, as the context vector, the error needs to go here first and then here, right? But now we don't need to do that. So the error directly backpropagate to all steps. So the model can learn which steps should be updated. Okay. But still, the model is not ideal. Why? Because the other problem is that the context vector is unique for all decoding steps. What do we mean by that? So we use one context vector, and then we feed it to each step in the decoder. So meaning that at each step in the decoder, or at each step in the decoding phase, we look at the input text equally. So we don't care what we want to generate. In any sense, we assume we have one context vector. But we know that at any decoding step, the decoder should focus on tokens of the input sentence differently. The main idea comes from the machine translation, that when we want to generate a word, or when we want to translate, or when we want to generate a word in the target language, we need to focus on different parts of the input sentence to generate that word, to generate a word. So how can we deal with this problem? So the main idea is that instead of you computing the mean, or like, let's say, the sum of the input states or hidden states in the encoder as the context vector, and then we use the context vector for all hidden states in the decoder, we can use some attention mechanisms. By attention, we mean that at each hidden state, we compute a specific context vector for that hidden state. So let's say at the first decoding step, we want to compute the context vector for this step. So we say the context vector for this step is the sum over the hidden states in the encoder, but we don't want to look at these hidden states equally. We want to focus on some words or some tokens or some parts of the input text more than the other tokens. So we instead of computing normal sum, we compute weighted sum. So we assign some weights to different hidden states, and then we compute this weighted sum of hidden states in the encoder, and then we use it as the context vector for the first decoding step. Okay, now that we generated the first token, we can take the first token as the input, and we concatenate that with the context vector that is specifically computed for the second hidden state. At the second hidden state, the context vector is computed as a weighted sum of the hidden states in the encoding state. So C2, or the context vector in the second hidden, or the context vector in the second decoding step equals to the weighted sum of the hidden states in the encoding phase. So we used alpha to refer to these weights, and the first index in the alpha shows the which decoding step we are, and the second index shows the encoding step. So we assign a weight to each encoding hidden state, and then we compute the weighted sum over these hidden states. And for the third step, we compute a specific context vector, and which similarly equals to the weighted sum of the hidden states in the encoding phase. Okay, now the question is, okay, so if we want to move to the formulation, to some mass, so we can see that the context vector equals to the weighted sum of the hidden states in the encoding phase. And in this equation, n is the number of tokens in the input sentence, or let's say the number of states in the encoding phase. So if you have an input, if you have 100 steps in the encoding phase, n equals to 100. So what you do is that you assign a weight like alpha to each step at the decoding phase. And let's say for step t, we have alpha t, and you want to, and at each step you also compute a weight for each hidden state. Okay, and how should we calculate these weights? the weight alpha T and for the, like at decoding step T and for hidden state K in the encoding phase equals to the softmax over some scores. Let's say what we do here is that we assign some scores to each hidden state. And how do we assign this score? That's another topic. But let's say we have some scores, let's say 5, 2, 1 or something. Let's say we have a function that assigns a score to these hidden states at the encoding phase. But in order to make them some sort of smoothly effective for our training, we compute the softmax to map these scores to some probability numbers, right? So let's say we have a score function over all encodings, a score function that returns we have a score function that returns some numbers for all hidden states in the encoding phase, and then we use a softmax function to map these scores to some probability distributions. So somehow the softmax function makes these weights or this score normalized. So okay, so the scores can be any numbers, but when you use softmax, we make them normalized. So when you sum them up, you kind of have normalized numbers. Okay, another question is how should we calculate the score? Scores is a function that takes the hidden state of the decoding phase in the previous step and the hidden state of the encoding or encoder at the current step. So meaning that if you want to generate this context vector for example, this one for hidden state in the third step of the encoding phase. So you use this hidden state and you use this hidden state in the decoding phase and give it to the score function, and it returns some scores for all hidden states in the encoding phase in here. So we can define different types of score functions. The first, and based on the way that you compute these score functions, you may get to different attention mechanisms. The first idea is to use context-based attention. Here, by clicking on the notes on the citations, you should be able to see the paper. So you can click there and you can download the paper and read the paper if you want. So in the content-based attention, the main idea is that the score function for a given hidden state in the encoding and a given hidden state in the decoding phase is the cosine similarity. So we say that the cosine value between these two vectors represents how similar or how related these two vectors are to each other. And if they are related, so probably we want to assign higher weights or higher, we want to focus on these encoding step more than others. The second approach is additive attention. In this approach, you use a neural model, mainly a multi-layer perceptron, to compute the score. So you concatenate the hidden state of the input, the hidden state in the encoding phase, and the hidden state in the decoding phase, and you concatenate these two vectors to each other, and you give it to the first layer of a multi-layer perceptron with tangent hyperbolic as the activation function, and you use the output and give it to the second layer in your multi-layer perceptron without any activation function, and as the output you will get some scores. So you leave it to another neural model like multi-layer perceptron to compute these scores for you. The third type is location-based attention. In the location-based attention, you compute the score using a softmax over the hidden state, over just the hidden state that you want to decode. So the idea is that you are using the context vector as the input to the hidden state in the decoding phase, right? So the hidden state, so it's more or less about the position when we want, or at which step we want to decode a number, or we want to decode a word. If we are at the second position, then the hidden state in the decoding phase may contain all the necessary information because the context is directly fed to this step as well. So what we can do is that the main idea behind this location-based attention is that we use a linear layer to map these hidden states in the decoding phase to some numbers over different states in the encoding phase. And then we use softmax to map these numbers to some scores or weights, or maybe we don't need the softmax here. We don't need the softmax here, and we only have these numbers because we define it separately in former slides. Okay. One of the important and also recent types for computing the score is a scale.product attention, which is defined based on the memory architecture in computer science that we define some key and query and value. We will see that in the next lecture completely, but just here when we talk about the transformer architectures, here I want to just touch it and just say how the attention works here. The main idea is that the score function can return the similarity between the context hidden, the decoding hidden states and the encoding hidden states. And for computing this, we can use dot product. So what we do is that we have HK, or the hidden state at the encoding step, and we have the vector of hidden state in the decoding step, like HTD. And what we do is that we do the time product. The trans is the transpose operation. So because we have two vectors, in order to be able to compute the dot product, we need to transpose one of these vectors, and then we do compute the dot product. The output of the dot product is like the similarity between these values. Okay, what is the scaling factor root n? The scaling factor is motivated by the concern when the input is large. So when you are computing the dot product, you are multiplying these numbers and sum them up. So when you are summing up some numbers, if the length of the vector is too large, then you may end up with a very, very large number, right? But in order to normalize it and not get to the large number and reduce the impact of the vanishing and gradient problem, so you use some a scaling factor based on the length of the input vectors, like the length of the hidden state, to reduce the impact of large numbers. Yeah, okay. Yeah, so when the values is large, the softmax function then returns very small values, small gradients, and then small gradients yields difficulties in learning. Good, good. But again, I emphasize that n here is the dimensionality of, then here is the dimensionality of the hidden state. So nothing more. Okay. Okay, so far we always define attention for a specific task that we are going to solve in the decoding phase. So if we are doing machine translation, the attention works for the machine translation. If we are doing sequence tagging, then the attention looks at the input for sequence tagging. So what I want to say from this aspect is that attention really depends on the task that you are solving. So attention doesn't learn which word is important or not. Attention learns which part of the input is important to solve a task. So if you want to generate and if you want to translate a sentence from one language to another language, then which part of the sentence should be more important at each decoding phase. But we as a human, when we read a text, we may pay attention to different part of the text differently. So we are not translating that, just we are reading that. So something like reading comprehension. When we want to understand the text, we may focus on different part of text differently. If we focus on one piece of text and we compute attention only for that part of the text, it's called self-attention. And self-attention is an attention mechanism to relate different tokens of an input sequence to compute a representation of the sequence itself. For example, the self-attention mechanism enables the model to learn the relations between a word of an input sequence and its previous words. Here is a nice example from Cheng and colleagues. And as we can see here, let's say the sentence is the FBI is chasing a criminal on the run. The colors in the words in the red color show which words we are reading, and the heat map actually with the blue color show that which previous word or which word previous to the word written in the red is more important when we are reading that word. When we read there is nothing before that, so we don't need attention. But when we are focusing on FBI or when we are reading FBI, the model pays attention to because it's the only word, of course. And the other reason could be that we have a phrase like the FBI. When we read is, then the model focuses on FBI. So given a noun phrase like the FBI, the model focuses on the main noun in the phrase, which is FBI here. When we say the FBI is chasing, both FBI and is apparently are important to the verb, like chasing. When we say a criminal, or when we read the model focuses on chasing, and so on. And when we finish the sentence, we get to the dot part. We see that chasing, criminal, run, or mainly the verbs criminal, chasing. I'm sorry, chasing. The verb chasing is very important, and also criminal and criminal who is on the run actually are important. Okay, so in this way, you can also define self-attention, where you use each token as the anchor to compute the importance of the previous token. And this model, like self-attention, can be very helpful for co-reference resolution, for machine reading comprehension, and this sort of tasks. Okay, let's talk about different applications. Probably the most obvious application is neural machine translation. So that in which we are given a piece of text like a Persian cat as the input in English, and we want to translate it into the German phrase like eine böse Katze. So what we do is that we use the input, we give it to the encoder, and we use some attention mechanism to compute the context vector. We map these context vectors to some hidden state in the decoding phase. And the task of the decoding is to generate the words in the German language. It can also be used for summarization. So we are given as the input, we are given the first sentence of the article, like Russian defense minister, and so on. And then our goal is to generate a headline. So we are given a piece of, we are given a sentence or one article, and we want to generate the headline as the summary of the text. And the good thing is that, so we, in this architecture, we don't move to different languages. So we still stay in English, but the difference is that the output text shouldn't have equal meaning to the input text. It should have the summary, or it should contain main information from the input text and present it only, and let's say compress it in only one sentence. And here we can see a nice heat map over attention. This heat map is very helpful actually for analyzing your model, and also to do error analysis, to say that like how your model works, where your model focus on, if it works properly or not, and if not, how you can make it better. The other application of these encoder-decoders is image caption generation, where the input is an image, and the output is going to be a caption for that image. So for example, if the input is the image that's on the left, what we want to generate is something like a bird flying over a body of water. So the main difference here with the previous architecture that we discussed is that the input is not a text. The input is an image. So you can use this encoder-decoder architecture to work on multimodality. So when you are working on different modalities, of course, you need to have a specific encoder for each modality. For example, here we have input image, so RNN cannot be that much useful. So you can use CNNs, for example, to extract features or your context vector. And when you have this context vector, you can give it to RNN-based decoder, and then it generates words for you as the input. As the output, or as the caption. You can train this model then end to end. Okay, you can use this. Of course, we can use it for other applications like lemmatization, where the inputs are characters. So you process characters one by one, and then you want to generate characters. You generate the characters one by one again as the output in the decoding phase. You can use this model, or you can use the encoder-decoder architecture for the spelling correction, where the input can be something like incorrect spelling of love and you. But since to show that where the space is happening, we use underscore to represent a space. And then, so as the input to the encoder, you use the incorrect sentence or a sentence with dictation error, and the output is the correct sentence. And you can train it using an end-to-end fashion, end-to-end learning fashion. Okay. So far, we discussed that an encoder-decoder model transforms an input sequence to some sort of other input sequence. So when we discussed that input text or input and output are usually different. So for example, in machine translation, the input text is in a source language and the output text is in a target language. Or in the summary generation, the input and output text are in the same language, but they should represent different things. So the source language or the source input text is the input text is very long and contains many sentences, many words, but the targets or the output text should be very short and contain main or key information of the input text. Or in image captioning, they are totally different. So the input is an image and the output is text. So they are in a totally different modalities. So in autoencoder, the main idea is that the input and output text or the input and output can be identical. So we are given a piece of text, for example, and we want to encode that to a vector, and then we use this encode to generate the text again. So the output text is exactly equal to the input text. So the main goal here is to learn the identity function f. So our goal is to learn if x equals to x. So the model can be easy if the hidden dimension is very long, right? So if you assume the context vector is very long, so you have like more than the number of tokens that you have in this sentence, then you can easily learn it. So you compress whole information here and in the context vector, and you can easily decode it. So it's like copy and paste. But if you reduce the size of the context vector, then you don't need to, then it gets difficult because you have some bottleneck. You want to compress this information, and then you want to decompress it again in the decoding phase. So what we can do is to make it to make the model learn this task easily, or let's say better, is that we usually add some noise to the input, then the model learns to remove this noise. So we can artificially add some noise. So just say when we are representing word embeddings, we can use some random noise or random values, and we then add this noise to the word embeddings, and then we give it to the encoder. Encoder map that to the context vector, and the task of the decoder then would be to remove this noise from the input embeddings. This autoencoder can be used for mainly unsupervised learning, because you do not have any label data, you have input sequences and you want to generate these input sequences again. And so it's sometimes called unsupervised learning. And it also can be useful for representation learning. So when you are given a text and you want to find the best representation for that, and one way of finding a best vector representation of the input text is to find a vector that can be decoded to the text again easily. So one way to, for example, there are some papers that have shown the best way to represent a paragraph is to map this paragraph to some hidden states, and then use these hidden states to generate the paragraph again. As we discussed, the encoder and decoder can be used individually to solve other tasks. So when you train this autoencoder to map from one sentence to itself, when you are done with this training, you can separate this model. You can use the decoder for the language modeling part, and you can use the encoder for the language encoding part of the encoder-decoder architecture. So in this lecture, we discussed about encoders and decoders. We discussed about different mechanisms, how we can encode and input text or image to some vectors, and how we can decode a vector to some text. We also discussed about attention mechanism, how we can focus on different part of the input text. We discussed about self-attention, in which that we only have one text, and we want to know at each, when we are reading the text, at which step we focus on which part of the text. And at the end, we also discuss about the applications of encoder decoder architecture and the attention mechanisms in NLP. That's it. Thank you for watching the video, and thank you for taking this lecture. Yeah, just please write your questions and feedbacks in the Moodle or in the YouTube comments. And yeah, and if you like the video, don't forget to like it, but you don't have to. See you later. Bye.